On this week's Arabidopsis Research Roundup, I'm delighted to be joined by Alistair McCormick from the University of Edinburgh. And this week we're going to be talking about a paper just published in New Phytologist, the title of which is Rubisco Small Subunits from the Unicellular Green Algae Chlamydomonas Complement Rubisco-deficient Mutants of Arabidopsis. So Alistair and I spoke about a year ago on a previous paper, and at the end of these research roundups I usually say I look forward to hearing how things have gone, how things go in the future. And this is a really great example of this. So this work really follows on from this previous work. So thanks very much, Alistair, for doing this again. It would be great if you could give us a little bit of background and then discuss what you went on to do in this paper, please.
Right, thanks, Garrett. Yeah, it's good to be speaking to you again as well. So basically this work really represents the next step of the CAP consortium's efforts to engineer a carbon concentrating mechanism into higher plants from the model green algal species Chlamydomonas. The CAP consortium stands for Combining Algal and Plant Photosynthesis, and it basically involves Howard Griffiths in Cambridge, Martin Yonicus in the States, who's recently moved to Princeton, and us in Edinburgh.
Okay.
So for what we've been focusing on this paper, as opposed to the previous one, which was engineering bicarbonate transporters into Arabidopsis, this time around we're focusing on trying to build a perinoid. So the perinoid in Chlamydomonas is the chloroplastic organelle where Rubisco is aggregated.
Okay.
So one of the first things we needed to do was to swap out the Rubisco small subunits from Chlamydomonas into Arabidopsis, as the small subunit in Chlammy is critical for getting Rubisco to aggregate together. This is work that was actually shown in Howard Griffiths' labs a few years ago. Okay. So what we did was we selected a Rubisco-deficient mutant, which we called 1A3B, because it lacks two of the small subunits in Arabidopsis. So it only has about 20 to 30% of the native amounts of Rubisco. And we then went about complementing it with a small subunit from Chlamydomonas, or a slightly modified one which looked a little bit more like an Arabidopsis small subunit, but still had the important parts from Chlamydomonas to get it to potentially assemble into a perinoid. Mm-hmm. So we engineered those into Arabidopsis, and lo and behold, they both worked very well. They both complemented plant growth, and they produced Rubiscos which were functional. And what was quite exciting about the work is that the versions of Rubisco which carried the modified small subunit, so this is the one with the Chlamydomonas parts, but were mainly native Arabidopsis otherwise, they had the same catalytic characteristics as native Rubisco. So that was really exciting. Okay. And sort of held promise for the use of this in further studies. The other thing which was quite exciting is that we went ahead and just put the Chlamydomonas small subunits straight into Arabidopsis, and that also complemented the plant, but the growth rates were slightly lower. Okay. And what we found when we looked at the catalytic characteristics of those Rubiscos, chimeric Rubiscos, were that they were basically slightly slower. And what was exciting about that is that it's first evidence that these small subunits actually influence the activity of Rubisco. Okay. Before this, I think there's a lot of evidence currently building towards this, but basically the small subunits are really passive, I suppose, holder of the large subunits. Right. And the idea that it actively affects the catalytic activity is quite exciting.
Okay. To follow up on that, I suppose, so the evidence that when you reduce the number of small subunits in Arabidopsis, you get much smaller plants, I guess that doesn't suggest anything about the catalytic activity, just the amount of Rubisco, is that right?
Exactly right. Okay. So the Rubisco is still exactly the same in those plants. There was just about 80% less than what you normally have. When we complemented them, we got it back to about 80-85%, if I remember the numbers. Okay.
Did you do any biochemistry in this paper to look to see if you were forming aggregates of Rubisco, perinoid-like?
We had a brief look. One of the reasons we think that they're not actually aggregating per se yet is that during the production of this paper, our colleagues in Martin Yonicus' lab came up with a beautiful BNAS paper which showed that there are additional components which are potentially chaperones in the perinoid, which act as the glue in between the Rubisco enzymes to glue them together. And this is a molecule called EPIC. Okay. It's a really fascinating protein. It's we believe it basically acts as to link possibly 4 different or more Rubisco molecules together. Okay. So now that we've built these chimeric Rubisco lines in Arabidopsis, what we're doing is we are looking at these other proteins like EPIC and other really exciting pronoid localized proteins that are coming out of Martin's lab to see if we can get this aggregation effect.
Okay, so are those EPIC proteins, they're clammy proteins, or they're
clammy, yeah.
Okay, so you're going to try and put them into Arabidopsis, see if you can squeeze them together. Oh, that would be very exciting. There's obviously a lot of strategies underway to try and improve photosynthesis, and it might be the most simple way of doing it, I suppose, if you can comment on that perhaps a little bit.
I suppose our advantage, we would argue, is that because it's a eukaryotic system, it might be the most compatible in that respect. One way we are disadvantaged, I suppose, is that the pronoid itself is still quite enigmatic in terms of all the proteins that are required to make it.
Right.
And they vary quite substantially between different algal species in terms of their structure and the components that make them up. So it's a bit harsh to sort of say that we have the main advantage.
No,
but I think we're making good progress.
Yeah, okay. It's a different strategy, certainly, trying to do a similar thing. Okay, so final question about the small subunits in Arabidopsis and Chlamydia as well. So you knock out a couple of genes and you get down to 30% of Rubisco function. So that suggests that they're unable to substitute for each other. Is that right?
So the small subunits, there are 4 small subunits in Arabidopsis, and they all express at different levels. So the 2 that were knocked out in the line that we worked with are the 2 highest, most highly expressed versions.
Okay.
So that implies that the promoters that drive the others are not powerful enough to get them to substitute as such.
I see.
We showed that those small subunits had a slightly increased level of expression, but nothing that would actually compensate for the overall loss of Rubisco that we saw.
Okay. And there's no evidence there's preferential formation of Rubiscos with different subunits in there?
So one of the other things that came out of the project seems to indicate that we had another small subunit plant that we made called 1A2B, which has alternative small subunits knocked out. So that grew slightly better than the 1A3B mutant, but was also, I think, only had about 40% of the Rubisco. Okay. When we looked at the catalytic activities of both of those plants, they were roughly the same, which indicates that the native small subunits probably don't play a substantial role in differential catalytic activities. Rather, they may, this is still up for grabs, but they may play a role in developmental changes or responding to different environmental stresses.
Okay, great. Okay, so sorry, we've gone off the topic a little bit there, but it's great. I like to give a little background in these little discussions as well. Okay, that's fantastic. Thanks very much, Alistair. And as I said, I said it last time, we look forward to seeing where this work goes. But I'll say it again, and this gets more and more interesting the more we learn, certainly. So thanks very much.